Hi, welcome to the Piezo-Metrics channel. I'm Frank and I'm here to talk about semiconductor strain gauges. In this video series, I'll provide some insights into semiconductor strain gauges, how to install them, and how they can be used. So, what is a semiconductor strain gauge? A semiconductor strain gauge is a crystalline material which, when stressed, will experience a distortion in its lattice structure. This means when the crystal is deformed, the distances between the silicon atoms will change, which in turn alters its energy band structure. This change in energy band determines the ease with which electrons or electron holes in the lattice can move around. The change in charge mobility results in a measurable change in the resistivity of the material. Even though the electrical resistance in a semiconductor strain gauge and a metal foil strain gauge both depend on the ease with which electrons flow through the material when the material is deformed, the actual mechanism of the resistance change is quite different for the two. To see what is going on, let's look at the atomic structure of a metal alloy, which is used in the metal foil strain gauge, and a doped silicon, which is used in a semiconductor strain gauge. Here on the left, we have a face-centered cubic structure that is representative of constantan. Constantan is commonly used in metal foil strain gauges. The resistance of the gauge is mainly determined by the constantan's conductivity and its cross-sectional area and length. Since conductivity as a property is independent of any shape change, the strain gauge changes resistance when it is deformed. For example, when a metal foil gauge is put into tension, its cross-sectional area gets smaller and its length gets longer. The result is that the resistance increases. Here I show the general equation for gauge factor. It is made up of two terms. The first term represents the contribution to gauge factor from a change in shape. Here nu is Poisson's ratio. The second term represents the contribution from the piezo-resistive effect. Here rho represents the resistivity. For a metal foil gauge, the gauge factor is typically around 2. Since the Poisson's ratio of constantan is roughly 0.3, we can see that shape change accounts for about 80% of the gauge factor. The remaining 20% comes from piezo-resistive effects, which are due to dislocation motions in the material. On the right, we have the atomic structure for a boron doped silicon. There's very little resistance change due to changes of shape in the crystal lattice. For semiconductor strain gauges, the gauge factor is dominated by the piezo-resistive effect. The result is that small changes in the crystal lattice results in large changes in resistivity, which gives large changes in gauge resistance. The much higher gauge factor in semiconductor strain gauges is a very desirable property from a signal generation point of view. The other advantage they have is that they can be made quite small. With standard foundry methods, feature sizes on the order of 2 micron are easily attainable. Here's a photo of a semiconductor strain gauge that is on top of a paperclip. The gauge measures 1.52 millimeters or 60 thousandths of an inch long. The paperclip is about 19 times longer than the strain gauge. Piezo-Metrics installs many of these gauges into high sensitivity, high stiffness transducers. The small size of the gauge is great if it can be bonded to a sensing element in a reliable way. It requires, however, a lot of manual skill to handle it without breaking it. We'll go over in a future video how to bond this strain gauge and how to solder the gold wires without melting them. A major inconvenience when working with semiconductor strain gauges is how to handle their high temperature sensitivity. For example, a semiconductor strain gauge can change 7 ohms per degree Celsius. This translates to a thermal strain of 3500 microstrain. For comparison, the thermal strain of a self-temperature compensated metal foil strain gauge is about 100 microstrain. Unlike the metal foil strain gauges, there's no way to formulate the silicon to be self-temperature compensating. The only option is to build temperature compensation circuitry outside of a Wheatstone bridge that uses semiconductor strain gauges. In this video series, we'll look at 2 types of temperature compensation techniques. One is based on a passive resistor network, and the other is based on a programmable signal conditioner. For this video, we will look at how a passive resistor network can temperature compensate a Wheatstone bridge that contains semiconductor strain gauges. Here's the layout of a Wheatstone bridge without temperature compensation. Imagine that the strain gauges are bonded to a pressure diaphragm. Gauges G1 and G3 are bonded to the center of the diaphragm, and gauges G2 and G4 are bonded to the outside diameter of the diaphragm. When a pressure is applied to the diaphragm, G1 and G3 are put into tension, and G2 and G4 are put into compression. The table shows the measured resistances of the gauges G1 to G4 at 0 and full scale pressure and at the cold and hot temperatures. We see that at the cold and 0 pressure condition, the gauge resistances are roughly equal to one another at around 430 ohms. The same goes for the gauge resistances at the hot and 0 pressure condition, where the resistances are roughly 560 ohms. In this case, the difference between the cold and hot temperatures is 55 degrees Celsius. At full-scale pressure for both temperatures, we can see that G1 and G3 go into tension because their resistances are increasing, and that G2 and G4 go into compression because their resistances are decreasing. When we calculate the bridge output for a 5-volt excitation, we can see that the full-scale output is quite high at over 300 millivolts, which is quite good. However, the pressure transducer in this state is not usable. The bridge does not output 0 millivolts at 0 pressure, and at full-scale pressure, the output is different when it is hot versus when it is cold. At cold, the output is 363 millivolts, while at hot, it is 330 millivolts. When we apply a temperature compensation solution to the Wheatstone bridge, we get this configuration, which incorporates a passive resistor network. I'll go over in a future video how the solution is calculated. We can see that 4 passive resistors have been added to the basic Wheatstone bridge. There is now a shunt resistor connected to gauge G1. This resistor has a value of roughly 35 kiloohms. There is also a series resistor connected to gauge G3. This resistor has a value of about 11 ohms. We have added a series resistor to the bridge, which has a value of 845 ohms, and a shunt resistor, which has a value of 976 ohms. When we look at the bridge output, we see that when the pressure is 0, the bridge output is now 0.7 to 0.8 millivolts at both the cold and hot temperatures. At full-scale pressure, the bridge outputs now a consistent 99 millivolts or so at both temperatures. So we can see from these results that a passive resistor network can tame quite well the temperature sensitivity of semiconductor strain gauges in a Wheatstone bridge. In this video, we have covered how a semiconductor strain gauge works and how a Wheatstone bridge that contains semiconductor strain gauges can be temperature compensated. In future videos, I will go over these topics in more detail, and additionally, I will show how to install and solder a semiconductor strain gauge, among other things. If you'd like to know more about semiconductor strain gauges, please visit the Piezo-Metrics website. The link is given below.